Okay, greetings, aspiring scientists. Welcome to my lecture today. I hope you're doing well. Today we're going to talk mainly about empirical formula versus molecular formula, and maybe get a little into balancing equations if we have time. So let's get right to it and go to my slides. So we are now in structure 1.4 to do with the mole, but specifically 1.4.4. This is empirical formula, molecular formula, and balancing equations. Balancing equations is not technically part of this in the syllabus, but I think it's about time we learn how to do this because a lot of practice questions involve having this skill, whether it's moles or ideal gases or concentration that are coming up soon. That skill is absolutely necessary to learn, I think, right now. Okay, so what is the empirical formula? So I have, right away, I'm just going to show you some empirical formulas and molecular formulas. There's 5 different ones on this slide: butane, water, hydrazine, hexanoic acid, and glucose. So what do you notice about the difference between empirical and molecular formula? That's what I usually ask my students, and they can give me the answer in a fairly short amount of time. What you should notice is that the empirical formula is sort of the lowest whole number simplified ratio of elements within the formula. Okay, so it's very similar to simplifying fractions. If you know something like, 4 over 8 can be simplified to 2 over 4, can be simplified to 1 over 2. You're bringing that ratio down, but it ends up being equivalent each time. It's just the most simplified form uses sort of the lowest whole numbers that we can use. So finding the empirical formula from a molecular formula is very similar to that. So we can look at the examples here. First, butane, C4H10. The empirical formula of that is C2H5. Okay, that's dividing the whole thing by 2. Now we can't go any further than that because 5 can't be divided by 2, or there's no sort of common factor between 2 and 5. We could try dividing by 5, but then 2 won't divide by 5 and keep a whole number, so we can't do that. So the empirical formula is set at C2H5. What about water? H2O? Well, the empirical formula is also H2O. Again, we can't divide one oxygen by any other number, so it's set at that. Sometimes the empirical formula is exactly the same as the molecular formula. Alright, hydrazine, N2H4, we can divide that by 2 to get NH2. Hexanoic acid, we can divide that by 2 to get C3H6O from C6H12O2. Just divide the whole formula by 2. And then glucose, C6H12O6. We can actually divide that whole formula by 6 to get CH2O, the most simplified ratio between those elements. Okay, so the empirical formula represents that most simplified ratio. The molecular formula, though, is the actual chemical formula of what actually exists at the atomic scale. Okay, so it's really the true representation of what a molecule is. So why do we really care about the empirical formula then? Well, when you do chemical analysis, say you go put your sample in some instrument, maybe it's like a bomb calorimeter or some kind of chromatogram or something, but what it will often spit out is the percentages by mass of each element that was contained in the molecular formula. So what it spits out from that, just the percentages, can give you the empirical formula, and we're going to go through that today and find out how it's done. But it's not as easy to get the molecular formula. Okay, you probably need to do more experiments, maybe mass spectrometry to find the actual compound's molecular weight. It often requires more steps. Okay, let's move on. Okay, the empirical formula is the most simplified possible ratio of atoms in the molecular formula, as I said. So I'm showing here how we divide each of the molecular formulas to get the empirical formula. Divide 2, divide 2, divide 2, divide 6, and water can't be divided. But you can divide by any number. It doesn't have to be 2 or 6, could be 3 or 4 or 5. Okay. So percentage composition by mass. This is also a really important idea. So modern instruments can easily break down a chemical into its atoms and measure percent composition by mass of each element. We can also do this mathematically with the formula, if we have the formula. So how do we do that? So let's take a random formula. Medium complexity one, H2SO4. So we want to find a lot of different numbers here. We want to find the total mass of H2SO4. So for that, we're going to take 2 hydrogens. And I'm just doing a rough calculation here, so I'm not using all the decimal places from the periodic table. I'm just taking that H is about 1 AMU, so 2 of that is 2 AMU. S is about 32 AMU. O is about 16, and we have 4 of those. So we multiply by 2 to get 64 AMU. So altogether, on the left side, that equals 98 atomic mass units, roughly, for H2SO4. So how do we find the percent composition by mass of each element? What you want to do is take those individual calculations that I did first and divide that by the total mass of the molecular formula. So that the whole mass of the molecular formula was 98. So for percent composition of hydrogen, we'll take 2 divided by 98, because there was 2 hydrogens of 1 AMU each. That gives us around 2%. What about sulfur then? Sulfur is about 32, so 32 over 98 is about 33%. And O, 4 O's, so that's 64 divided by 98, that's about 65%. And you just do want to make sure that that total adds up to 100%. Even though I'm doing rough calculations, there's a chance it might add up to, 99 or 101. So just round things so that it works out to 100% if you need. All right, so those are the percent compositions by mass of H, S, and O in the H2SO4 formula. You should be able to do that for any molecular formula that you have. And the percent composition by mass for the molecular formula and the empirical formula should be the same. So you can also use that, I believe. Because just multiplying something by 2 or 3 or 5 or whatever doesn't change this percent composition by mass. Alright, so let's get into how to find empirical formula from data. So just before we get really into this, I want to point out that there's a lot of different ways that questions can lead you into, requesting that you find the empirical formula, and lots of different information that they can give you that you'll be expected to use to get there. So in this first example, I'm going to show you one pathway. This pathway is probably the most common that you would see in practice questions or exams. So in this type, you are given some percentages, just like on the previous slide that I calculated, the percentage by mass of several different atoms or elements inside a formula. So determine the empirical formula of an unknown sample that was found to have 3.6% hydrogen, 12.3% nitrogen, 56.0% oxygen, and 28.1% sulfur by mass. Okay, and this question seems to indicate that's everything that's in the formula, only those 4. But sometimes they will indicate that there are 4 and then only give you 3 of the percentages. You're expected to know that they all must equal 100% when added together. So you could take 100 minus one of them, minus the second one, minus the third one, and that should give you the percentage of the 4th one. We might see that in practice questions later. Anyway, so there are 4 steps with this type of question that I'll recommend. First, now this is strange, and this really confused me when I was a high school student, and it might confuse you. And I'm going to ask you to assume a sample of this compound which has 100 grams, okay? Now, you might say, how or why would we do that? We've just been given percentages, okay? This question hasn't identified any particular sample, so that leaves us with the power to determine what the sample is, actually. We can just imagine any mass that we want. But you do need to imagine a mass, okay? You could imagine 50 grams, you could imagine 800 grams, you could imagine whatever, and still do this. But the reason why 100 is so powerful is because when you have percentages of 100 grams, you can just immediately convert those percentage numbers into gram numbers. Think about it. 100 grams, what's 12.3% of that? 12.3 grams. What's 3.6% of that? 3.6 grams. Okay, so you can just immediately change those percentages into a mass, a gram number. And that's so important because we need to get moles. And we only have really one equation that will allow us to generate a number of moles that we've learned in this class anyway. That's N equals little m over big M. Number of moles equals mass divided by molar mass. So whatever you do, you have to assume some amount of mass to be able to answer this. Okay, so step 1, assume 100 grams, total sample. It comes out of nowhere, okay? We're just imagining it. So for nitrogen then, 12.3%, we're going to have 12.3 grams, hydrogen 3.6 grams, sulfur 28.1 grams, and oxygen 56.0 grams. All right, next, step 2, convert all of those into moles immediately. So it's mass divided by molar mass. So mass divided by molar mass for nitrogen. Molar mass for nitrogen is what you see on the periodic table for atomic weight. It's 14.01. So dividing 12.3 by 14.01 gives 0.8779 moles. Write the units so you don't confuse yourself. Same thing for hydrogen, that's 3.564 moles. Same thing for sulfur, that's 0.8762 moles. And same thing for oxygen, 3.5 moles. And here's the thing about these type of questions and significant figures. Everything's going to be rounded to a whole number in the end, so you don't have to care about significant figures in this type of question. So I'm just writing a bunch. 4 should be enough to get this right. Alright, so we've got moles. Maybe you can see there is some kind of ratio between these, right? Like we've got 2 that are about 0.87 and 2 that are about 3.5. So those are probably going to have the same like subscript number in the final formula we get. But we need to get whole numbers. We can't have 0.87 because there can't be like 0.87 of one atom bonded in a formula, right? They have to be whole numbers of atoms. So there's a cool step you can do in step 3, which is find the lowest number of your step 2 calculations and just divide all 4 of these numbers, or however many you have, divide all of them by the smallest one. So this will set the smallest one to 1, exactly. And then the other ones should reform to a close to whole number, okay? So N will be about 1, 1.002. H will be about 4, 4.068. And O will be about 4, 3.994. Okay. So these are not quite whole numbers, and that will happen just because, you know, of the precision and significant figures of the numbers that we use and whoever measured these percentages also. So it's not going to be exactly right, but you need to then round these numbers. Okay, so 1.002 rounds to 1, 4.068 rounds to 4, 1 rounds to 1, and 3.994 rounds up to 4. And those numbers are the subscripts of the elements that will be in the empirical formula. So N is 1, H is 4, S is 1, and O is 4. Remember that we don't write 1s in the chemical formula. We just write nothing, and we assume that that means 1. So NH4, SO4. Now, some of you might look at that and say, that doesn't look like any chemical that I know, and in fact it looks wrong, because some of you probably know that the SO4 group has a charge of 2-, and the NH4 group has a charge of +1, and they couldn't bond together in this way. And that's right, but that doesn't mean all my information here is nonsense, because the real formula for that is NH4, 2, that should be a subscript, but 2 groups of NH4, and S2O8. All those numbers should be subscripts. But there's a special ion, S2O8, that has a 2- charge, and NH4 has 2 groups there. So you can see if you were to multiply the empirical formula that we found by 2, you would get that molecular formula in the top right. Okay, fairly standard question. It'll take you quite a while to do it at first, but once you get these steps down, especially like remembering to assume 100 grams, remembering to divide by the lowest number, you can do it really quick. Now, I will mention that there's a couple exceptions here. Things can go kind of wrong when you generate your first ratio numbers, your non-whole numbers. So I'll get into that a few slides later. So empirical formula practice, why don't you guys try this one? See if you can follow those steps and do this question. Okay. If you've done it, then I'll go to my whiteboard actually and see if I can do it myself pretty quick. So 26.4% carbon, 3.3% hydrogen, 70.3% oxygen. So I'm going to just make a little kind of table like I had on my previous slide. And I'll do step 1. That's to immediately change percentages into grams by assuming 100 grams of sample. So I will have 26.4 grams of carbon, 3.3 grams of hydrogen, 70.3 grams of oxygen. Okay, step 2. Change these into moles. So I'll need to divide by the relative atomic mass of each of these, C, H, and O. So C I'll divide by 12.01. I get 2.198. Again, don't care about significant figures too much. Hydrogen divided by 1.01, I'll get 3.267. And oxygen divided by 16, I'll get 4.394. Good. So these are the ratios that we're looking for. It's just that they're not whole numbers, and atoms must be whole numbers in a formula. So we have to simplify these. We'll divide by the lowest one. The lowest one is 2.198. So I'll just make a note here. I'm dividing by 2.198. So this one will set to 1. H should be 1.486. And O should be 1.999. Okay, so here we are. C is clearly 1. O is clearly 2. What about H though? Like, feels kind of bad to round that down to 1, doesn't it? That's a massive rounding. And that's right. Okay? If it seems too far away, then there's other things you actually need to try. Okay? So when you have something that's around 0.5 like this, whether it's 0.5 or 1.5 or 2.5 or 3.5, what I'm going to recommend that you do is multiply everything here by 2. Okay, remember that these ratios are already correct. It's just that we are trying to get these into the lowest possible whole number ratios that we can. And the way to get 1.5 to a whole number is to multiply it by 2. But if you multiply the middle one by 2, you have to multiply the others by 2 to keep that ratio. Okay, so do that. We'll get 2. I'm going to round that. For the other one, I'll get just under 3, but I'm going to round it to 3. And for oxygen, I'll get 4. Again, what I've done is just multiplied everything by 2. Okay, so that means my empirical formula for this compound that contains only carbon, hydrogen, and oxygen must be C2H3O4. That's the empirical formula. Alright, so what should you do here? Well, you know what the molecular weight or molecular mass of this formula should be. So what you should do is find out what the mass of the empirical formula that you found is. What's the empirical formula mass? You can just do this roughly as well. So the empirical formula mass will be about 2 times 12 for carbon plus 3 times 1 for hydrogen plus 4 times 16 for oxygen. And that's going to come out to, I think, 91-ish gram per mole, if I'm talking about molar mass. Alright, so what do you notice? 91 for the empirical and 182 for the molecular. Well, it seems like the molecular formula must be double, because 91 is exactly half of 182. And that's really what you should do, is just going to separate these here. Take your known molar mass of the sample and divide it by the empirical formula mass that you found. And this will give you your multiplier that links the empirical formula and the molecular formula together. So this ends up being 2. So I can say the molecular formula is exactly double the empirical formula, C4H6O8. And then you're done. Alright, so I know some of you more advanced people probably are wondering, what does the structure of this possibly look like? And I don't think it's possible to draw a structure of the empirical formula. It doesn't really make a lot of sense to have 2 carbons and 4 oxygens and 3 hydrogens. But it is possible to have a structure of this molecular formula. So what I think it is 4 carbons in a chain. The 2 on the end have carboxyl groups. And the 2 in the middle both have 2 hydroxyl groups. Like that. It's called like dihydroxytartaric acid or something. So that's a reasonable structure. I've drawn it pretty poorly, but there's nothing illegal about the bonding in this. I don't expect you to know what this is if you're just starting chemistry, but those of you who have studied organics later on and structures, you might recognize that structure. Or some parts of it anyway. Okay, let's go back 2 slides. Okay, what else? So, I want to talk about rounding a little bit, because you maybe thought it was strange that I multiplied one of those steps by 2 to get rid of a 1.5. So I think these are the general rules that I would follow if I were you when it comes to rounding or multiplying. So if the number that you get after you divide by the lowest number of moles is around something 0.9, like x 0.9 or higher, you can round up to the next whole number. So 0.9 goes to 1. If you have a number 0.75, 0.75, 1.75, 2.75, what you want to do is multiply by 4, because that 0.25 or the 0.75 will end up being a whole number if you multiply that by 4. If you don't believe me, go try some in your calculator. Multiplying by 4 should give you whole numbers. Okay, if you have x 0.66, some number 0.66, multiply by 3, that should solve your problems. If you have something 0.5, multiply by 2, 0.33, multiply by 3, 0.25, multiply by 4, and if you have 0.1 or lower, round that down to the nearest whole number. So 1.1, round it down to 1, 2.08, round it down to 2. Okay, hopefully you know what I mean on this slide. It's just some rounding advice and rules to follow. If you have numbers in between these that are not quite near it, just, do whatever's the closest. You have to do something. Okay. Practice questions then. Here's one. Deduce the empirical formula of an oxide of manganese that contains 36.81% oxygen by weight. Okay, maybe I can just do this on the slide here. So we only have one percentage here, right? MN percent, we actually don't know. O percent, we did know. 36.81. But this just says it's an oxide of manganese, so you can read that and sort of assume that oxygen and manganese are the only things in this formula. So without realizing that, you can't really go any further on this, but if we know that these two are the only two things, we know we have some formula that's going to look like MnXOY, and we're trying to find the X and Y numbers. So it must be true that the manganese percent is 100% minus 36.81%. Okay, and that ends up being 63.19% manganese. All right. So with that, you can do the whole empirical formula steps. So assume 100 grams, divide by the molar mass. So for the oxygen, you're going to do 36.81 divided by 16. And that's going to get you right around 2.301. For manganese then, you're going to do 63.19 grams divided by manganese. Go look on the periodic table. You'll find it's 54.94. And that comes out to 1.150. Alright, then we're at the step where we will divide by the lowest. So the lowest is 1.150. Okay, sorry. Divide by 1.150. This one will go to 1. And this one will go to 2. So super easy. This ends up just being MnO2. Okay, now I have other questions underneath here. So I'm going to erase a lot of this on the right. Okay, so let's see what else we have. So part B, deduce the empirical formula of a hydrocarbon that produces 5.501 grams of CO2 and 2.253 grams of water upon combustion. And another part of this, deduce the molecular formula of the hydrocarbon from 1B if its molar mass is 42.09 gram per mole. Okay, I think we have to go to the whiteboard for this. So this question requires a little bit of background knowledge to be able to answer, I think. Okay, our whiteboard. So what you need to know is a specific type of chemical reaction. This is called a combustion reaction. I'm sure you know what combustion means, like burning, right? The internal combustion engine powers cars and vehicles. So what we're doing there is burning a fuel to release energy. And what comes out the exhausts? Well, it's carbon dioxide emissions, and it's also water and potentially other things if it's not complete combustion. But just for today, what I want you to remember and realize is that a very common chemical reaction occurs. A fuel, usually this is a hydrocarbon. That means it contains only hydrogen and carbon, plus oxygen gas, O2 gas, combusts to produce CO2 and water. Okay, so probably this is a formal part of the curriculum and the syllabus in later topics like organic chemistry and fuels, but we really need to learn this because it also shows up a lot in stoichiometry and moles and ratios and things, chemical reactions. So it's a good time to learn it now. A fuel plus oxygen gas goes to CO2 and H2O. Okay, and our question said somebody detected 5.501 grams of CO2 and 2.253 grams of water. So this is an empirical formula question, but we're coming at it from a different angle. We don't immediately have percentages this time. What we have instead is products of a chemical reaction. But you need to realize that you still have all the information you need to find an empirical formula. What you need to try to get is mole ratios, right? We're trying to find what this hydrocarbon fuel was. It's CXHY. X and Y are something. And we can find it with this information. But if this is the first time you're seeing this kind of question, it can be really hard to start. But just do what you can do, right? You have masses, you have chemical formula of two products here, CO2 and H2O, so immediately convert those into moles. So 5.501 gram, we will divide that by the molar mass of CO2. That's 1 carbon, 12.01, plus 2 oxygens, 16 each. That ends up being 44.01 gram per mole. And that will be 0.1250 moles. Okay, what about water? 2.253 grams. Divide that by the molar mass of water. Remember, N equals M over M, little m over big M. So 2.253 grams divided by the molar mass of water, that's 16 plus 1.01 plus 1.01. This ends up being 18.02. And that will be 0.1250 moles, also the same. Okay, so we have 0.1250 moles of each product, but then we're kind of stuck, right? We can't just divide by the smallest here, because this CO2 and H2O don't mean exactly the ratios of carbon and hydrogen in our starting materials, our fuel. Remember, this is the fuel. But they do have a connection with the fuel, okay? Look at CO2. Inside of CO2, there's 1 carbon and 2 oxygens. Those 2 oxygens must have come from the O2 gas on the left side of this equation. So we don't really worry about that. And the 1 carbon atom in there, all of that carbon must have come from the carbon in our fuel. Okay, so whatever number of moles of CO2 we produced, that must be equal to the amount of carbon atoms, or the mole ratio of carbon within the formula of our fuel. Okay, so this X must be 0.1250. We'll try to get it to a whole number later, but let's figure out H next. So look at H2O. There are 2 hydrogen atoms in the H2O molecule. But none of those came from O2. All of those must have come from our fuel. Our fuel is a hydrocarbon that contains hydrogen. So all of the hydrogen atoms in H2O must have come from our fuel. But here's the thing. What's the ratio of hydrogen to water inside of the H2O formula. That ratio is 2 to 1. Okay? If you have one particle of H2O, you have 2 particles of H inside. If you have 1 mole of H2O, you have 2 moles of H's inside. So there's a ratio of 2 to 1 here. Alright, so if we produce 0.1250 moles of water, that water contains double that, which is 0.250 moles of hydrogen. All of that hydrogen must have come from our starting material fuel. Okay? So that's kind of a very difficult idea, but this is one of the key things to solve many problems in IB chemistry. To find the ratio of things in a chemical formula and within a balanced chemical equation and within a chemical formula. Okay, so I know that Y must be that ratio of 2 over 1, multiplied by moles of H2O. And I can actually write that here to make it clear. Two hydrogens per 1 H2O multiplied by 0.1250 mole of H2O. Okay, so maybe I shouldn't write hydrogen specifically. I'll write mole of H so that these cancel out properly. Particles and moles are directly proportional, so we could use either one, but just to try to make this clear, I want these moles of H2O to cancel out, and I'll be left with moles of hydrogen, which is double the moles of water. 0.250. Okay. Now, we've ended up in sort of step 3 or step 4 of the empirical formula guide that I gave you in the first slides of this video. So what you can do now is just divide both of these by the lowest one, 0.125. And what you'll get is x is 1 and y is 2. So empirical formula is CH2. All right. So quite a long ways to get there. You have to realize the combustion formula, where all of the hydrogen and carbon atoms came from, the mole ratios between those things. A lot of people will get confused at doubling the hydrogen amount of moles to get the original amount of hydrogen from the fuel chemical formula. But if you need to, go and watch what I said again. Okay, and then the last step was, how do we actually get the molecular formula of this fuel? Those of you who know about structure know that CH2 is not really possible as a formula, so it's probably not that. So what's the molar mass of CH2, this formula? 12.01 plus 1.01 plus 1.01, that ends up being 14.03 grams per mole, or AMU, whatever you want. Alright, and then in the question, This was technically question 2, I think, on the slide. It says our molecular formula, molar mass, was 42.09. Alright, so that's quite a bit larger than 14.03, but how many times larger exactly? Do the division. Maybe you can see it immediately, but oftentimes I can't. I'm not really that good at math. This ends up being triple. Okay, 3 times 14.03 would give us 42.09. So we can just triple CH2, that empirical formula. So molecular formula is C3H6. Done. Alright, let's go back to slides. Okay, so the answers are then given on the right side as I calculated. Moving on. So I do want to just review and expand on the concepts of ions a little bit. It's going to become really important. Atoms can have an electric charge that's written in a superscript on the top right. Electrically charged atoms are called ions. We know this. Ions bonded together with more than one atom are called polyatomic ions. If you know the poly prefix, it means many of something, so many atom ions. So regular ions that we've seen are like Na plus, O2 minus, but now I'm going to introduce polyatomic ions like SO4 2 minus. So positive ions are called cations, negative are called anions. That has not changed. So SO4 2 minus, even though it's polyatomic, is still an anion. These things are just going to start appearing in some chemical formula, so I think it's good that I introduce them. So before I finish this video, I do want to show a chemical formula, each part of it, and how to balance it. Okay, so here's a pretty simple equation. This is the first lab work that I do with my classes. Magnesium plus oxygen gas goes to magnesium oxide, MgO. So on the left side you have some elements. Mg is an element, O2 is an element. On the right side you have a compound, MgO. Then the red lines will show the state of matter of these things. So we're talking about solid, liquid, gas, or sometimes aqueous. Aqueous is AQ, meaning dissolved in water in a homogeneous solution. Then in front of these formula, we have what are called mole or particle ratios. They tell you how many of this particle needs to, react with other things to make this reaction go forward. So we need 2 magnesium atoms, and we need 1 O2 molecule. There's nothing written in front of O2, but we understand that nothing means number 1. Okay, so that means 1 particle of O2. That will produce MgO. What else is in here? We've got these orange lines, number of atoms. So again, for O2, that's the subscript 2, indicates there's 2 oxygens. They are bonded together in this formula. Everything else, though, doesn't have any numbers. There's nothing on the subscript of Mg or O or MgO. So we understand those also mean 1, okay? If there's no number, it just means there's 1 of that. Okay, so the numbers in the front, the mole or particle ratios, you can change in order to make sure that this is balanced. Okay, so if the 2 was not written in front of, Mg and MgO, it would be your job to look at this and realize that they must be there to have conservation of matter, okay? Things cannot disappear or be created out of nothing. So it must be true that whatever is on the left side has equal numbers of atoms on the right side. So you can look at this, 2 magnesiums on the left, 2 on the right, they are equal. 2 oxygens on the left, that O subscript 2 indicates 2 oxygen atoms bonded together. And then 2 units of MgO, that also contains 1 oxygen atom each, so that's 2. So they are balanced in that way. It's your job to balance these chemical equations. All right, moving on. So here's my advice for balancing. First, balance elements which are not hydrogen or oxygen. This could be a lot of things: potassium, sulfur, sodium, chlorine, whatever. Second, balance any packages of polyatomic ions. Oftentimes polyatomic ions will stay as they are and they'll not break apart. Not always, but things like sulfate and nitrate and what else? Phosphate, they're pretty stable. So oftentimes they'll stay as a unit and just you count the units of that. You can call it X or whatever if it's confusing you, but it's just a unit that doesn't change. Next, balance any hydrogens. Third step. All right, step 4, redo step 1, 2, and 3 if necessary. Oftentimes when you balance hydrogens, you might throw off some of the previous balancing you did. So just make sure that everything is balanced up to step 3. So step 4, then balance oxygen last, especially if you know that there's O2 in the equation. Something's combusting maybe, or oxidizing with O2. You can change the particle or the mole number of O2 to almost anything you want to, make it balanced in the end. So can we see some examples? H2SO4 plus KOH goes to K2SO4 plus H2O. And C4H10 plus O2 goes to CO2 plus H2O. Why don't you try to balance those? You can maybe do it quickly in your head or write it down. Okay, if you gave it a shot, I'll write what I would do. So H2SO4, KOH. So right away I can see that the SO4 polyatomic ion, sulfate, will stay as a unit in this. It doesn't break apart. And I see that I've got potassium, that's K. And I'm going to start with that because that's not a polyatomic ion unit. It's not hydrogen, it's not oxygen. So with K, I see I've got 1 K on the left and I've got 2 K on the right. That means I absolutely must have at least 2 units of KOH. Alright, so when I've done that, I can make sure that my sulfates are balanced, my polyatomic ions. I have 1 on each side, 1 on the left, 1 on the right. Then hydrogens. How many hydrogens do I have on the left? I've got 2 in H2SO4, and I've got 2 in 2 units of KOH. That's 4 total. On the right side, though, I only have 2 in H2O. So I know I must double the amount of H2O to balance my hydrogens. And with that, you'll actually find this equation is balanced. All right, we've got 2 oxygens, not including SO4. So 2 from KOH, 2 from H2O. Oxygen is balanced. And hydrogens are balanced. We've got 2 in H2SO4, 2 in KOH, 4 on the left total. And then 4 on the right in 2 molecules of H2O. So that's done as it is. C4H10 on the bottom then. So start with things that are not oxygen or hydrogen. That means carbon in this case. So C4, 4 carbons on the left. That means I must have 4 CO2 at least. All right. What else can we say? So hydrogen next. There's no polyatomic ions in this formula. But hydrogen, we've got 10 on the left and only 2 on the right. So I will need at least 5 water molecules to make 10 on the right. Now I've got 10 on each side. All right, now what else can I do to fix this? Now, oxygen lasts according to my steps advice. So on the right side, we've got 5 in H2O and then 8 in 4 units of CO2. So we've got 13. Now, here's the problem. This is O2, and if we want to get 13 oxygens, we would have to write a fraction in front of that oxygen. We would write 13 divided by 2. But unless otherwise stated, I think you should always write these balanced chemical equations with only whole numbers in front of those chemical formula. So in cases like that, I would recommend multiplying the whole equation by 2. Multiply the whole equation by 2. So you can take what I had and just multiply it by 2. But that will include the first thing here, double that. So CO2 was 4, it's going to become 8. H2O was 5, it's going to become 10. And O2, we would have written 13 over 2, or 6.5, but we want whole numbers. Luckily, doubling this has made it so that I can just write 13 here. Okay, so I believe that is the simplest way to balance this equation with the lowest possible whole number ratios. 2 C4H10 plus 13 O2s produces 8 CO2s and 10 H2Os. Okay, so this is a really important skill you have to do very often. I think I have a little bit more practice on following slides. Yeah, here's another one. Ethine C2H2 reacts with oxygen gas in welding torches to produce CO2 and water, H2O. Write a balanced chemical equation for this reaction. You should be able to do that fairly quickly. Again, this is a combustion reaction of fuel plus oxygen. In this case, our fuel is C2H2 plus oxygen gas goes to CO2 and water. So start with balancing the carbons. We'll need at least 2 of that CO2. Then the hydrogens. It's already balanced. But when we get to the oxygens, we might run into this problem again. We've got 5 on the right and then O2 on the left. It's going to create a fraction. So I'll rewrite this and multiply everything by 2. So 2 C2H2. I was going to write 5 over 2, or 2.5, but instead, multiplying everything by 2, I can write this as 5O2. I'm not writing states here, I just don't think it's that important. So I had 2 CO2, it's going to actually become 4 when I double it. And I had 1 water, but I need to double that as well. Okay, so I had to double this to get whole numbers. And then that should be the balanced equation with the lowest possible whole numbers. Alright, any other practice? Yes, a whole bunch of practice. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different equations you can try to balance with varying degrees of difficulty. Remember that sometimes they're balanced already, so don't bash your head against a wall trying to balance something that's already balanced. Alright, I do have the answers for these, the solutions, so I'll show it on the next slide. If you don't want to see it, don't look, but coming in 3, 2, 1. Alright, here's my answers for how to balance these 9 equations. Okay, so again, balancing is not really a part of this empirical formula section, but it's going to become a part of, almost every unit's questions, so that's why I just thought it was good to teach that in today's lesson. Alright, next time we'll move on to concentrations and making solutions and titrations. Long video today, but hopefully you enjoyed it and learned something or got some practice. That's all. Have a good one. See you next time.